web, on the left side, you have the link, polev.com/risky. So please join via web because our activities will be using polev to take lecture participations, basically. So it's polev.com/risky. Oh yeah, actually, the other thing is that it will be, so you have to be registered in the polev, and you have to log in with your NUS account, because without that, it will not work. So make sure to log in with your NUS account when you open this link. Okay, I think probably let's get started because it's already 4 p.m. So welcome to the introduction to AI and machine learning. So this is the first lecture. So again, like my warning, after you log into the polev.com, which is at polev.com/risky, this link over here, make sure to not close your web browser, okay? Because we'll have activities ahead. Okay, so before we start, I think probably a good idea to introduce the instructors for this course. So there are 4 instructors in this course. So first is me, Risky. I think maybe I should introduce a little bit about myself. So I'm a lecturer in School of Computing, and my research interest is in deep reinforcement learning. We also have Chong Hui. I'm not sure whether Chong Hui is in here. Yeah, Chong Hui is there. So Chong Hui is the other instructor. So her specialization, her research interest is in deep learning, computer vision. We also have Patrick, which is in here. Research interest is in quantum machine learning. And we also have Eric. I don't know whether Eric's in here. Probably not, yeah. Which works in machine learning on high-dimensional data. And we have a bunch of teaching assistants. In fact, we have, I think, 30-something teaching assistants for this course because there are so many of you who joined the course. It's a core module, after all. So these are the teaching assistants. So if you, later on, once you are assigned to a tutorial, then you can have a look at this slide again. So I'm just going to put it in here. Make sure to not copy or to not share these slides or any materials because it is violation of NUS rights. Okay, so I think, yeah, for those of you who are just settling in, you can just go forward. I think it's good to fill up the front first because we have so many empty seats at the front. So please fill up the front first. Yeah, so I think maybe the first thing that I want to do is I want to motivate you on why you should actually learning AI and machine learning. Why do you actually want to learn AI and machine learning? So let's go through that. So I'll have a little video over here.
It's going to eliminate a lot of current jobs. That's true. We can make much better ones.
You know, I've always thought of AI as the most profound technology humanity is working on. More profound than fire or electricity or anything that we have done in the past.
It's one of the things that, the sort of 4 or 5 things I thought would really affect the future dramatically.
I think it's comparable in scale with the Industrial Revolution or electricity, or maybe the wheel.
Or maybe the wheel.
Yeah.
So this is as big a breakthrough, a milestone, as I've seen in the whole digital computer realm.
The threat is huge. We're on the edge of a precipice, and I'm not trying to be too dramatic here.
As we've made these things bigger and bigger, they keep emerging with new capabilities. We have not figured out how powerful this technology is going to be yet.
I hope that many other small business owners take advantage of this technology because AI is creating tremendous wealth and will continue to create tremendous wealth.
It is a renaissance. It is a golden age. We are now solving problems with machine learning and artificial intelligence that were, kind of in the realm of science fiction for the last several decades.
Perhaps the most important foundational technology of our time, artificial intelligence.
It'll acquire all knowledge there ever was, okay, rapidly.
Hang on to your hats, ladies and gentlemen, because what did my friend Jonathan Pajot say? Giants are going to walk the earth once more.
Yeah, I know some of them are
It is going to eliminate a lot of current jobs.
Yeah. So I know some of them are quite bombastic, but please bear with some of them. Some of the statements are pretty good, and those statements are coming from, like famous people, basically. Some of them are researchers. Some of them are like head of some companies. So, and this is also another video that I want to show you. I think most of you maybe like have seen this video before. This is the revealing of ChatGPT 4.0, which is the latest iteration of ChatGPT. I think it's quite interesting.
Hey, how's it going?
Hey there, it's going great. How about you? I see you're rocking an OpenAI hoodie. Nice choice. What's up with that ceiling though? Are you in a cool industry-style office or something?
Well, can you take a guess at what I might be doing based on what I'm showing you here?
From what I can see, it looks like you're in some kind of recording or production setup. With those lights, tripods, and possibly a mic, it seems like you might be gearing up to shoot a video or maybe even a live stream.
Yeah. In fact, we've got a new announcement to make.
That's exciting. Announcements are always a big deal. Judging by the setup, it looks like it's going to be quite the professional production. Is this announcement related to OpenAI, perhaps?
It is. And in fact, what if I were to say that you're related to the announcement, or that you are the announcement?
Me? The announcement is about me? Well, color me intrigued. Are you about to reveal something about AI? Or more specifically about me as a part of OpenAI? You've got me on the edge of my, well, I don't really have a seat, but you get the idea. What's the big news?
Yeah, we've got a new model that can interact with the world through audio, vision, and text.
Yeah, so I think, don't you want to understand like how these things work? The things that maybe some of you already use, like the ChatGPT, and maybe right now we have ChatGPT 4.0, which you could interact by speech only. Yeah, sorry. Sorry, repeat that again. Zoom. Doesn't like what? Oh, yeah, there is none, yeah. So we're still figuring things out, yeah. So basically there will be no, okay, let's talk about the course matter later on, okay? So now I'm just trying to motivate you guys first. So if you are interested in knowing more about this course basically is the first step if you want to understand more. And if you want to have a look into more pragmatic reason on why you want to learn about AI, right? So first, software development. I think most of you are probably going to be a software developer in the future. So these days, software development has been dramatically changed over, if you compare it with, say, 10 years ago. Now, software development involves AI. You probably worked with GitHub Copilot and those things, right? So I think learning the underlying principle about how this AI actually works, it's very important because it could help you understand what it actually can do and what it actually cannot do, and how actually you could interact with AI, with this technology better as well. And not to mention that companies are now pushing AI into all their products. We have Microsoft pushing it into Windows. You have Windows Copilot. There is Microsoft Copilot. You have Apple Intelligence. You have QChat if you use Quizlet. There is Netflix as well. There is also, Figma AI. You could generate, design by simply typing what you want. You also have Slack with their own AI as well. But basically, like companies nowadays, they have AI in their products, like AI infused in their products, no matter whether the products are related to AI or not. And companies are expecting you, maybe like future software engineers, right, to be able to at least know about AI. And if you understand like how these things work, then you'll have like some edge among the competitors, like other people, basically. And then the other thing is, more importantly, right, you could throw a bunch of AI technobabbles, so you could sound smart. So for instance, your friend said, ChatGPT will take over our job, bro. And then you say, nah, ChatGPT will be, I don't know, like high-dimensional manifold shift, meta-optimization, whatever. It doesn't really matter. It doesn't really even make sense, but at least you could sound smart. I'm just joking, by the way. This is obviously a joke. Yeah. So more seriously, right, if you learn how machines actually could learn, then probably you would be able to learn about how to learn itself. Like learning how to learn is very important, especially in software development. Okay, so hopefully after looking at watching the videos, after being given the facts that companies are pushing AI left and right, hopefully you're may be more interested in learning about AI, so I think it's probably a good time to introduce about the course. So cs2109s is basically an introductory course designed to cover fundamental topics in AI and machine learning. It's a basic introductory course. And there are things which you should expect, and there are things which you should not expect. You should go with the right expectation, basically, with 2109s. So what to expect is we will be covering like quite a wide range of topics, introductory topics in AI and machine learning. We will also be covering some practical knowledge in terms of how you could actually implement some AI and machine learning algorithms. We will also be covering like ways for you to could actually apply these technologies and to solve problems. And you will also be exposed to conceptual understanding on how this AI and machine learning works. However, you should not expect that this course will be very mathematical, very rigorous, very theoretical. This course is like very introductory course, so we will probably not going to cover a lot of proofs, if there is any. And there will be no extensive coverage of the recent advances in AI. So maybe something like ChatGPT 4o, how does it work? Probably will not be covering that. But at least steps towards learning that would be given to you. So these are features, by the way, not bugs. And the prerequisites, I'm sure you have already known about this, but the main idea is that you will need to learn to know about trees, graphs, counting, combinatorics, differentiation, chain rule, tree, graph search, factor matrix, and their operation, basically. And Python as well, because your problem sets will be on Python. And for these two things, right, linear algebra and Python, we will be covering it in our optional problem set 0. So if you're interested in learning more about it, then you could work on the problem set 0. So the overview of the course is going to be something like this. So we will be covering, like during the first 3 weeks, we'll be covering a classical AI. So that'll be from week 1 until week 3. And I will be the one covering the classical AI. And we'll be talking about all kinds of different search algorithms, like uninformed search, local search, informed search, and so on. You will know about all this later on. And after that, these things basically are just applied CS24TS and use of Python and so on. From week 4 until week 8, we'll be learning about classical machine learning, classical in quotes. So I will be delivering the first introduction to machine learning lecture, and afterwards Patrick will be taking over and teach you about the rest of the classical machine learning, which will be covering decision trees, linear logistic regression, and support vector machines. And we will have midterm at week 7, which is during the lecture time, subject to successfully securing the venue. And afterwards, we'll be learning about modern machine learning. This traditional and classical and modern machine learning, I just put it there based on like what people consider to be modern these days. Okay, and we'll be covering about neural networks and deep learning basically, and then that's up to week 11. And Chong Hui will be the one covering this topic. And finally, we'll be covering like miscellaneous stuff until week 12, which is Patrick and me is going to cover this miscellaneous stuff. And we'll talk about unsupervised learning, practical machine learning, AI, and ethics. So this second, like classical machine learning, modern machine learning, basically just applied linear algebra, calculus, statistics, and probabilistics. And then at the final week, we will have a final exam. The date, I think you could have a look into it in the SOC schedule. Okay, so I want to highlight some of the changes because some of you might have heard about CS2109s from your friends, for example, who have already taken the module. This semester we'll be revamping quite a lot of it, so there will be quite many changes in the course, so I'm going to highlight some of those. So one is the final assessment. We will not be having the 28 hours final take-home assessment anymore, but we'll have the normal Exemplify exam instead for the final assessment. And the weighting for the midterm and final, there will be, from 35%, we'll be putting it down to 30%. Problem sets, previously we had 9 problem sets. Now we are reducing it to 5 main problem sets, and then 2 optional problem sets. These 2 optional problem sets, you don't actually have to do it if you want to get into level 30, but it's good to do it because it's useful for you in terms of gaining knowledge. And you can also get like additional EXPs, maybe if you want to skip some other things. And we also have new contest, which is 10%. And again, we have lecture participation, and we'll be giving out EXP based on your participation at lecture. So the textbook that we're going to use, but there's no need to buy these textbooks, basically is the AI A Modern Approach, 4th edition. And we will be using cosmology. Some of you haven't been invited to cosmology because you came late, basically. We will be running the scripts to import your data from Canvas to cosmology later on, so don't worry. And we'll be using Canvas for only gradebook and maybe webcasts. So like recording things, it will not be in Zoom, it will be in Canvas. Okay, so this is very important, the collaboration policy, the course policies. So the collaboration policy for this course, you can have a look into it in the link below. But basically, these are the collaboration policy. Very important for you to take notes of this. So you can only discuss ideas. You cannot do anything else apart from discussing ideas. Even if you discuss ideas, you have to cite the discussions that happened. And it is also okay for you to, for instance, like find some codes online and then use that codes in your parts of that codes into your code, as long as you cite the code. And the code is not part of the solutions that you're trying to, it's not itself a solution, basically. And you should not share, you should not consult, you should not discuss or use part or essence of the solution, maybe from your friends or from the internet, through any means, like spoken words, whiteboard, video, or whatnot, even after you're done with the course, basically. So this is quite stringent restriction, but we have this after, like 2 years of experience dealing with plagiarism cases, basically. So that's why we have these very, very specific rules in here. And do not view and use other person's solution and use it as basis of your own solution. So if you have any doubts, you can simply just contact us in the instructors, and we'll let you know whether your actions are okay or not. AI policy. So the AI policy between different modules are different, and in this particular course, we will have a very lenient, very relaxed AI policy. Basically, you can use AI as long as you have proper citations. So if you could share the conversation link, then you should share the conversation link. If you could not share the conversation link, then you should take the screenshot of that particular conversations that you have with your AI, and you document any changes that you have made to the AI code, so we know like what exactly is happening. And the citation must be included in the references section in your submission. So in your submission, you will have like references section, you put it there. And if you use AI-generated code, right, do not alter the AI-generated code unnecessarily or obfuscate it in any ways. It's fine. Just copy-paste it is fine. Do not obfuscate it because it makes it even more, I don't know, like it just makes us like feel like maybe you're trying to hide something, okay? So do not do that. Plagiarism. Any plagiarism or academic dishonesty will be reported to UG. No matter how small it is, you only plagiarize maybe one assignment or maybe one question in one assignment. It doesn't matter. We will be we'll be escalating the problem into UG office. Any plagiarism check will be performed against all the previous batches. So we have currently, I think, 2 years plus of batches. So we'll be running across all of those. And the potential penalty based on the UG office is like this. So this is just a warning for you to not do anything funny. If it is more than or equal to 10% in terms of the weightage of the assignment, then it's automatic fail, and plus other things. And if it is less than 10%, then maximum penalty that you get is probably reduction in letter grade. So maybe from A to B, B to C, and so on. Yeah. And this is decided by the UG, by the way. It's not by us. And the assessments, we'll have these assessments. We have cosmology component, which is probably all of you will get 30%. We'll have contest 10%, midterm 30%, final exam 30%. And basically, this is just for your reference, right? This is probably wrong because it really depends on the cohort, but this is roughly what you'll expect. So the 30% here, this will be free. So everyone will get this 30%. And then what you have to do is you get an additional 20%, and you probably will be getting something which is better than F. And afterwards, like if you do like another 15%, you get maybe a C or something. But again, this one depends on the quality of the cohort, just for guidelines. And for the gamified CA, 30% basically is you have the lecture, and in the lecture you could gain up to 300 EXP, and then you have lecture training, which is like short quizzes, maybe like 10 questions, very easy, 150 EXP, and 50 EXP early bonus. We also have forum EXP, so whenever you participate in the forum, then you'll get additional EXP, up to 100 EXP. And you have tutorial EXP, which is 500 EXP, and problem set you get every 2 weeks. So now we have 5 problem sets, so quite relaxed, hopefully, around 2,000 EXPs. And extra stuff like background survey, which is 100 EXP. And if you have enough EXP, let's say, I don't know, like 1,000 EXP means you level up from level 0 to 1, then you level up. And whatever level that you reach at the end, maybe you'll reach level 30, then your CA grade will be 30%. If you reach level 45, for example, then it doesn't matter, it will be 30, because it will be not more than 30. And for the lecture, 100 EXP will be free. So as long as you come and then you participate, doesn't matter whether your answers are correct or incorrect, it doesn't matter, you'll get 100 EXP. 200 EXP based on your performance, and if you answer like 10 out of 10 questions correct, then you get 100% and so on. And you will have, maybe sometimes you'll have contests just for fun, and you'll have leaderboard in that contest, but it doesn't really matter, the leaderboard doesn't matter. What counts is your correctness in your answers. And the tutorial will be, the EXP will be given by your TA, and it will be between 250 no participation and 500 EXP. And we also have, the other thing is the contest, which is 10% here. This is for you to have a chance to explore what's out there, like being able to implement and apply your knowledge into solving like real world problems. And in here, the idea is basically we'll be developing some kind of AI agent to solve some games. We will be revealing the game later on. You can use any techniques that you want, and your AI will be pitted against one another, and then your AI performance will be the one used to grade you, basically. And then just for fun, the top performing one will be showcased at the end, via some tournament, and we'll give out some prizes. So, hopefully it will motivate some of you. And the duration, we'll set it to be around 2 months so that you have plenty of time to work on this. Midterm and final, closed book, open sheet, but it doesn't really matter because it will be more or less like applications, like conceptual understanding. So even if you have books in front of you, it doesn't really matter. And midterm is 30%, this is the date and time. Final is also 30%, this is the date and time. So make sure to reserve these dates in your calendar. Late policy. So up to 1 hour, it will be 0% late policy. So you could be late, you could be submitting your PS at 12:30 and you should be okay. But if you submit up to 24 hours, maybe you submit like 8 hours late, then it will be 20% penalty. 3 days, 30%, beyond 3 days, 50% penalty. If you need an extension, maybe like you have some, I don't know, like some problems, maybe you're sick and you have proper valid AMC, then you could let us know about it and we'll extend accordingly. Okay, so there are some common mistakes that students that took cs2109s makes usually, and that could cause them problems in terms of, like finishing things quickly. So one is regarding to the debugging. Like a lot of people, since the way we're giving out the PS is via Jupyter Notebook, right? A lot of people actually really like to debug their codes in Jupyter Notebook by printing a lot of things, and that's not a good idea. You should use Visual Studio Code or other IDE, so proper IDE, because otherwise you'll spend too much time like dealing with debugging with a proper debugger. So you should do this for PS0 and all non-machine learning problem sets. The other thing is a lot of people do not really like documentations, and I do understand that it's painful to read documentations, but it is very useful for you to read documentations if, for example, we ask you to implement things using NumPy, because there are a lot of built-in functions, and you would benefit from it, basically. And many people also like to code in Cosmology. This is not a good idea because Cosmology is not an IDE. It will take time for Cosmology to process the request and then to get back to you. And it's possible for you to lose your progress as well, so do not do this, okay? Okay. Okay, yeah, we have Q&A here. Do not use it. Use Cloudy 3.5 with artifacts. Is that sure? Yeah, whatever you want to use, it's okay. Yeah. If you have any questions, you can write it in your poll EV, or you can simply ask the questions. That's fine. I'll be answering the questions, but I will not take too much time in here because we have a lot of other things to cover. Yeah, go ahead. Well, then probably you have to cite the conversations, and we would know that you are sharing the conversations. No, don't do that. That's not a good idea. We will, huh? I mean, I think, right, the best idea for you, right, to be very, very reasonable. Do not try to find exploit because that doesn't work. So for example, right, like the idea on passing the conversation to someone else and then use that conversation, for example, that you know that that's wrong, right? So don't do it, okay? So be reasonable with yourself. Do not lie to yourself. This is not okay, and you should not do it. But if you have any trouble, any questions, feel free to ask us, and we will clarify with you whether your actions is okay or not. Remote lecture options for students. I look good, thanks a lot, everyone. Are there remote lecture options for students unable to attend physical lectures? There is a webcast. So you can have a look into the webcast, but there will be delay, which is, I think, a 1 minute delay or something. And that's not good because during the poll EV session, you will not be able to participate. And your participation point probably will be, I don't know, like either small or will be 0, yeah. Unless you keep on looking into your poll EV, yeah. Is contest compulsory or is it bonus 10%? Compulsory, so you have to do it. It's 10% of the total grades. If I'm an AI, then do I have to cite myself? Interesting, I didn't know that we have AI joining today. How is point awarded for contest, winner take it all, or just participation? 10% is a lot. We'll be revealing more details about the contest later. Yeah, I think it's done. How do I score A+? Yeah, okay, I think probably good. Let's move on. Okay, so now let's talk about intro to AI, okay? So we'll be talking about all these things. These are like the more important topics than the previous topics, which is what is AI, a brief history of AI, intelligent agents, and so on. So now let's talk about what is AI. And in particular, maybe let's talk about some examples of AI. Maybe, I doubt it, but maybe some of you do not know like some examples of AI. So ChatGPT will be one example of AI. You also have, Gary Kasparov in 90-something is beaten by AI called Deep Blue. We also have AlphaGo by Google DeepMind just recently beaten Lee Sedol. I think it was in 2017 or something, I don't remember. And you also have the IBM Watson, which beats people in Jeopardy. These are some of examples of more bombastic AI, like AI with a lot of exposure. We also have AI in the form of self-driving car. Like for example, the Tesla has this autopilot software. We also have AI that could draw images for you, like the one in the Bing image creator. There is also AI that detects things, for example, oh, this is my phone, this is like pen, paper, and so on. Now, what is AI? Why don't we just simply ask AI, right? So I asked AI about what is AI, and ChatGPT actually answers me this way. Artificial intelligence is the creation of computer systems that can perform tasks and make decisions similar to human intelligence. I think the answer is pretty good, So this is probably like one of the definitions that you would come across, what is AI. There are also other definitions of AI in the book that I'm referring to, this from the 2nd edition. We define AI as the study of agents that receive percepts from the environment and perform action. So an agent that receives percepts maybe through the eyes or whatever, and then like do something with that percept, like in the environment to perform something useful, that's called AI. And John McCarthy, which is the one who coined the terms AI, said that AI is basically the science and engineering of making intelligent machines. So these are like some textbook definitions of AI. Now, before we move forward to the intelligent agents, how we could actually design intelligent agents, maybe good to have a look into a brief history of AI, right? So the history of AI starts at the beginning. At the beginning of the universe, as far as I know, there is no AI research. And after some times, I think people start thinking about artificial life forms. I think it was in some, I don't know, like 10 BC or something. They start to think about artificial life forms, and in the year 1000 something, people start to really think about like what AI is. And there are some advances, but there is really not much happening because there were no computers. In 1900s, we start to have computers, and then ABC, computer could solve linear equations, so that's one potentially example of AI. And people started to develop this thing called artificial neurons, which later today becomes the deep learning, the system that is under that is the one that powers ChatGPT. In 1950s, we have Alan Turing describing Turing machines and Turing tests, basically a test to distinguish between AI and computer. There's also AI that could solve checkers game. There's also Lisp programming language, which people love to use to build AI back in the days, and ELIZA. In 1970s, we have the first AI winter because people kind of disillusioned with the capability of AI. They thought that AI could solve everything, like companies are jumping left and right, but then turns out it was not able to fulfill the promise. So they had the AI winter. This AI winter, basically, some research are still being done, but not really substantial. In 1980s is the rise of expert systems, basically systems that uses some kind of formal reasoning to be able to deduce something based on a bunch of facts, basically. So those are like the popular AI back in the days. And people even come up with this thing called fifth generation computers, like computers designed to be running these expert systems. And in 1990s, we have Deep Blue, which is based on search algorithms, which could beat Garry Kasparov. Moving forward, in 2000s, we have the second AI winter. The reason is because a lot of companies back in the day, like during the fifth generation computers, they thought that, oh, AI finally could replace doctors, could replace human being in terms of driving and so on. AI are thought to be able to solve everything, basically, at that point in time in 1990s. But then turns out it wasn't able to fulfill the promise, so companies start pulling off from the AI. And we have the second AI winter. And then during this time, there is like internet blows up, and people now have this thing called big data, because like a lot of data are shared on the internet and so on. And we also have like DARPA Grand Challenge, where like DARPA wants DARPA has to have a contest where you could participate and build a self-driving car machine, basically. In 2010s, AI start to pick up again. We have to start to see deep learning systems, although like deep neural networks has been invented like way before in 19 something, but like now it's gaining popularity. And we have IBM Watson. We start having like assistant like Apple Siri, Google Now, and so on. In 2015 is the year of deep reinforcement learning. So everybody is doing deep reinforcement learning. Google came up with AlphaGo, AlphaStar. AlphaGo could solve Go problems. AlphaStar could play StarCraft games. OpenAI come up with this thing called OpenAI 5, which could play Dota games. So people love to play with games back in the 2015. And in around 2015, I think 2017 or something, Transformers was invented, and GPT was also invented, which is the precursor to ChatGPT. And then in 2020s is the year of generative AI. Everybody's doing generative AI. There's ChatGPT, there is DALL-E, Stable Diffusion, Sora. Like this generative AI could generate anything, like videos, text, audio, anything. And we have now multimodal generative AI, like the ones in ChatGPT 4.0. We also have a lot of AI in consumer products, like Apple Intelligence, like Google, everything like been infused with AI. So that's mostly like a brief history of AI. Now that we know a little bit of history about AI, and we know, like what is AI, I think before that, I know it's early, but maybe we could take a quick break, because why not? Yeah, let's take a quick break, I think. Yeah, and watch this video, I think. So this is a break, by the way. It's 5 minutes break, so you can go anywhere, but if you want to have a look at a video with me, you can do that.
In the coming years, artificial intelligence is probably going to change your life, and likely the entire world. But people have a hard time agreeing on exactly how. The following are excerpts from a World Economic Forum interview where renowned computer science professor and AI expert Stuart Russell helps separate the sense from the nonsense.
There's a big difference between asking a human to do something and giving that as the objective to an AI system. When you ask a human to fetch you a cup of coffee, you don't mean this should be their life's mission and nothing else in the universe matters. Even if they have to kill everybody else in Starbucks to get you the coffee before it closes, they should do that. No, that's not what you mean. Right? You mean all the other things that we mutually care about, they should factor into your behavior as well. And the problem with the way we build AI systems now is we give them a fixed objective, right? The algorithms require us to specify everything in the objective. And if you say, can we fix the acidification of the oceans? Yeah, you could have a catalytic reaction that does that extremely efficiently, but, consumes a quarter of the oxygen in the atmosphere, which would apparently cause us to die fairly slowly and unpleasantly over the course of several hours. So how do we avoid this problem, right? You might say, okay, well, just be more careful about specifying the objective, right? Don't forget the atmospheric oxygen. And then, of course, some side effect of the reaction in the ocean poisons all the fish. Okay, well, I meant don't kill the fish either. And then, well, what about the seaweed? Okay, well, don't do anything that's going to cause all the seaweed to die. And on and on and on, right? And the reason that we don't have to do that with humans is that humans often know that they don't know all the things that we care about. If you ask a human to get you a cup of coffee, and you happen to be in the Hotel Georges V in Paris, where the coffee is, I think, 13 euros a cup, it's entirely reasonable to come back and say, well, it's 13 euros, are you sure you want, or I could go next door and, get one. And it's a perfectly normal thing for a person to do, right? To ask, I'm going to repaint your house. Is it okay if I take off the drain pipes and then put them back? We don't think of this as a terribly sophisticated capability, but AI systems don't have it because the way we build them now, they have to know the full objective. If we build systems that know that they don't know what the objective is, then they start to exhibit these behaviors, like asking permission before getting rid of all the oxygen in the atmosphere. In all these senses, control over the AI system comes from the machine's uncertainty about what the true objective is. And it's when you build machines that believe with certainty that they have the objective, that's when you get the sort of psychopathic behavior. And I think we see the same thing in humans. What happens when general purpose AI hits the real economy? How do things change? Can we adapt? This is a very old point. Amazingly, Aristotle actually has a passage where he says, look, if we had fully automated weaving machines and plectrums that could pluck the lyre and produce music without any humans, then we wouldn't need any workers. That idea, which I think it was Keynes who called it technological unemployment in 1930, is very obvious to people, right? They think, yeah, of course, if the machine does the work, then I'm going to be unemployed. If you think about the warehouses that companies are currently operating for e-commerce, they are half automated. The way it works is that an old warehouse where you've got tons of stuff piled up all over the place and the humans go and rummage around and then bring it back and send it off, there's a robot who goes and gets the shelving unit that contains the thing that you need. But the human has to pick the object out of the bin or off the shelf because that's still too difficult. But, at the same time, could you make a robot that is accurate enough to be able to pick pretty much any object? And there's a very wide variety of objects that you can buy. And that would, at a stroke, eliminate 3 or 4 million jobs. There's an interesting story that E.M. Forster wrote where everyone is entirely machine dependent. The story is really about the fact that if you hand over the management of your civilization to machines, you then lose the incentive to understand it yourself or to teach the next generation how to understand it. And you can see Wall-E actually as a modern version where everyone is enfeebled and infantilized by the machine. And that hasn't been possible up to now, right? We put a lot of our civilization into books, but the books can't run it for us. And so we always have to teach the next generation. If you work it out, it's about 1 trillion person years of teaching and learning and an unbroken chain that goes back tens of thousands of generations. What happens if that chain breaks? And I think that's something we have to understand as AI moves forward. The actual date of arrival of general purpose AI, you're not going to be able to pinpoint, right? It isn't a single day. It's also not the case it's all or nothing. The impact is going to be increasing. So with every advance in AI, it significantly expands the range of tasks. So in that sense, I think most experts say by the end of the century, we're very, very likely to have general purpose AI. The median is something around 2045. I'm a little more on the conservative side. I think the problem is harder than we think. I like what John McCarthy, who was sort of one of the founders of AI, when he was asked this question, he said, well, somewhere between 5 and 500 years, and we're going to need, I think, several Einsteins to make it happen.
But how will the economy change in the meantime? Will it be able to keep growing? What?
All right, welcome back to the course. So now that we actually have a break, I think it's a good idea to have some quiz. So let's have some quiz. So everyone, please open your Poll Everywhere app. So this is the link, by the way, pollev.com/risky. So make sure that all of you have opened it. pollev.com/risky. Okay, so now let's get started. So the setup now is that you discovered a GitHub repository with solutions from someone who took the course last year. Yeah, some of them are cropped, I don't know why. Which of the following actions are allowed? So you found someone else's GitHub from maybe like taking like cs2109s last year. So which of the following actions are allowed? So we'll have a look into each action and you should answer it in your phone, okay? Copy parts of the solutions and cite the source. So you'll have, I think, 20 seconds. For some reasons, it didn't show up in there. Yeah, there's something wrong with PollEV, but yeah. Yeah, I cannot really see, actually. Yeah, so it's done because it says activity is now locked. So let's have a look into the answer. So the answer should be not allowed, obviously. You should not copy-paste things, right? So you should not copy parts of the solution it's really odd that I think 50% of you said it's allowed. Okay, let's continue on. This is the leaderboard, but I think there is a bug. Yeah, I think PollEV has been very buggy today. But anyways, yeah. The next thing is whether it is okay for you to review the solutions, then write your own code and cite them. Yeah, please answer it in your mobile phone. Okay, it's done. So the actual answer is it is not allowed. That's really odd. You guys seen the policy, right? You actually cannot look into the solution. So reviewing a solution means you have to look into the solution, so that's not allowed, so you should not do it, okay? Next. Oh, this is the leaderboard. Now we have a leaderboard. So David Z is the leading person now, followed by Gong Yi. Okay, the next one is ask ChatGPT to write the solutions for you. Is it allowed or is it not allowed? Okay, so yeah, it's not allowed because you cannot actually ask ChatGPT to write solutions for you because it means that you are deriving solutions from someone else's solution. Yeah. So in fact, we actually have this kind of cases before and we caught them, so that's not a good idea. And now last is avoid using code and report it to your instructors as potential code sharing violation. Is it allowed? Okay, it's done. Now, that's really odd. What is going on? Okay, yeah, so it is allowed actually for if you avoid it. So actually, like the rule of thumb, right? If you just come across like someone else's code, please just just leave it. Do not come close to it. Do not even look at it, right? Just go and then report it if you can, because like this code should not be there in the first place, okay? Okay, so this is like the winner, basically. Ian Q, H, Hans Delano, Isaac, and Skylar, and Tiwari Pranay, yeah. They are the winners for this one. It doesn't really matter, by the way. This leaderboard is just for fun. Okay, now we have another one. Okay, yeah, what is the format of our final exam? Okay. Oh, that's really odd. Like, for some reason, people think that it's take-home exemplify. Oh. Take-home exemplify exam. Okay, yeah. And anyways, like for some reasons, some of you believe that it's take-home exemplify exam. Some of you believe that it's programming exam. This is not true. So the exam this semester, we change it into exemplify offline. So you'll have to come to a venue and then you do the exemplify yourself. I think it's a good idea for me to put in this quiz because now I know that some of you actually didn't get it. So yeah. So yep, I think that's all. Okay. So now that we are done with the quiz, yeah. Now let's get back to our main topic again, which is on intelligent agents. So now that we know what is AI and we know a bit of history of AI, I think it's a good idea for us to start now to look into how we could actually design AI or intelligent agents. So now, right, like how do we actually design an intelligent agents? So the way we design intelligent agents first is for us to be able to look into what components, what necessary components that we have to have when we're trying to solve a problem with AI. First, the first component would be for us to know like what's the environment of the AI, right? So where is it actually the AI being deployed? And from there, we should also know about how the AI would be able to get its input, right? So the sensors of the AI. So maybe this is a self-driving car problem. We want to make a car that could drive itself. So maybe like the sensors for the car to be able to take in information from the environment. Maybe it's from LiDAR. So we have LiDARs and like a bunch of cameras. So these are like the sensors of our agents. After the information are being fed to the sensors, like those informations must be processed, right? So there must be some kind of machine, some kind of computer, some kind of function that take in all those information and process it and knows what to do. So basically, inside of this self-driving car, usually there is an onboard computer. So it's like some kind of computer on board. And this onboard computer contains some kind of function, like AI function, which does things, like decide whether, oh, it's a good idea for now, after looking into this input, it's a good idea to move forward, it's a good idea to move right, it's a good idea to move left. After the AI know what to decide, then what happens is the AI will need to be able to perform actions, right? So there need to be some kind of way for the self-driving car to be able to interact with the environment, right? So in this case, it will need an actuators. So an actuator in the self-driving car will be maybe the wheel, right? So it has 4 wheels. Maybe it has like front wipers, back wipers. Maybe it has some other things which like controls the car. Maybe the AC, whatever. So that's what the loop looks like. So when we design intelligent agents, we have to look into all these vectors. Not only that, we also have to look into like how we could actually assess the performance of our AI agent. In this case, this is a self-driving car. How do we know that this self-driving car agent actually is a good self-driving car agent? We have to be able to kind of quantify, like know the quality of our AI, right? So that's why we need some kind of performance measure, right? So the performance measure, we have to be able to measure it, how good the AI is. So let's say, oh, like whether it's jerky or not, like whether, like if it sees a human being over here, it doesn't just hit the human being, like the safety factors. So those things we have to incorporate in our AI agent. And that should be in our design when we're designing AI. So to put it more formally, basically we have this kind of feedback loop when we are designing AI agents. We have this thing, which is the environment, and environment gives out data about itself through percepts, and it is taken by the sensors, and the sensors will process the data and then like pass it into the function. So this function will be doing some AI magic, and will output the actuators and finally give it back to the environment. So there will be like this established loop in our intelligent agents. So now there is there is one framework that we could use, like in terms of defining like what's the environment, sensors, actuators. So this formalism is called PEACE, which is performance measure, environment, actuators, and sensors. So in this case, like performance measure, it's very important, and usually we should consider quite a number of things. For example, whether the performance measure is best for whom. Is it best for the AI? Is it best for like other agents inside of the environment? Because it affects the performance of the agent. What are we actually optimizing? Are we trying to optimize like the speed of our agent? Are we optimizing safety? Like those factors we have to take care of. What is the information that is available? So like maybe we want to take in like the 360 sensor information. Maybe we just want to take in like the forward information and so on. And intended effects. Maybe, for example, maybe if like if we just focus on speed, then what happens is like all the people are dead because they get hit by the car, for example, right? What are the costs and so on? So a rational agents. So this is just a definition, by the way. So we have a definition of a rational agent. So a rational agent basically is an agent, is an AI agent, which given this performance measure, no matter what it is, like that it is measuring, it will try to optimize the performance measure by doing actions that are maximizing this performance measure. So I think maybe good idea to, again, like based on this framework, re-look into our self-driving car example. So in the environment, in this case, the environment, right? We will have a bunch of things in the environment. We take in like the light, like we have cars, we have maybe human beings, maybe we have trees, we have the sky, we have the weather condition, like all those things are available in the environment of the self-driving car. And in this case, the percepts, it's coming from the LiDAR, it's coming from the sensor data. So that would be like the image of the environment. Maybe it also has like some kind of LiDAR information, right? So those things are coming in as the sensors, and it goes straight to the function, and the function output in actuators. And the actuators would be, for example, like how much steers that you have to do. Like, do you want to like steer left, or do you want to steer right? Like, or do you want to like push the pedal forward, or you want to brake it, or like those things are the actuators. So we have the environment, we have the actuators, we have the sensors. And what about the performance measure in this case? The performance measure would be, the safety, for example. If there is a human being over here, do not run over it. The jagginess of the car, like instead of like moving very erratically like this, it's good to be very smooth about it. Maybe the speed. We want to make sure that the car is like very, very fast, like it reached from destination A to destination B like really quickly rather than like going somewhere first, for example. So these things are like the performance measure for the self-driving car, just as an example. What about AI assistant or chatbot? Any ideas? Let's start from the performance measure. Any idea what kind of performance measure that we're looking at? I've given an example in self-driving cars, so it's time for you to have a look into this. Any ideas? The quality of the answers, correct, right? So like this chatbot, right, we want to get some kind of information from it, right? So whatever it's right here, then it should be of good quality. So that's one performance measure. Anything else? Yep. Speed of response, correct. So for example, right, it is able to spit out the very, very good response, but it takes in, let's say, 7 million years, right? So that's not acceptable at all. So we want to make sure that it's, maybe less than, I don't know, like less than 200 milliseconds or something like for the response, right? So these things are very important. Not only it has to be good, accurate, it also has to be fast as well. Any other like potential performance measure for this problem, AI? Anything else? Yeah, go ahead. User ratings. Sure, yeah. So at the end of the day, like we care about like the user, right? Whether like these things are good. But usually, like this user rating, they are related in some way with the quality of the answer and the speed of the response, right? So probably you could break it down even further. Like these things, like what is the performance measure that we're actually measuring in the user rating? Yeah. So there are a bunch of them. So let's move on from the performance measure. What about the environment? Like, what is the environment in this case? What are the informations inside of the environment? Yeah. The prompt. Sure, yeah, the prompt is part of the environment. So the user are, giving out prompts, and like the prompts are taken into consideration usually when you're making decision. Anything else? Anything else? It might be surprising, but the user itself, it's also part of the environment because the AI actually is interacting with human, right? So the human is actually part of the environment as well. So that's quite interesting, right? So there are also other things. For example, this one is residing in some kind of operating system, right? Maybe this is like Apple OS. And also like there are other apps. Maybe like there is like these apps, like this is part of the environment of the OS and so on. So there are a lot of things going on in the environment. What about the sensors? What are the sensors? Any ideas? What are the sensors? The keyboard, yep. So the keyboard here is the sensors, right? The sensors basically are things to capture, like information from the environment, right? So the keyboard is one of them. Anything else? Yeah. The camera, yeah. So this camera will be able, like in GPT-4o, it will be able to look around and like comments about the environment. So yeah, camera would be one of them. You also have the microphone and other things, yeah. What about the actuators? Oops. Actuators. The screen, yep. So the screen, like that gives the information to the user is part of the actuators. You also have the sound, for example, right? So like it'd be able to like say something, for example, like GPT-4o, and many other things. Maybe it has access to some kind of API, so it will be able to like interact with the web or something, right? So these things are part of the actuators. Now that we have done talking about the peace framework, right? I think it's probably a good idea to know what the environment that we're looking at. In particular, it's probably a good idea to try to categorize the environment that we have so that we could work on it depending on the properties of the environment. So let's have a look into the environment. So there are a bunch of different properties of environment that the agent could actually live in. So one is with regards to the observability of the environment. So an environment could be fully observable or partially observable. So what does it mean? It means that if the environment is fully observable, it means that all the informations that are available, they're available to the agent. If it's partially observable, it means that like some of the environment might not be available for the agent. So for instance, let's say we have a look into this problem, right? We have chess. In chess, all the pieces are the agent actually could see all the pieces, right? All the pieces information, like what are the empty spaces. The chess could see everything. All the informations that are in the chess, they're available, right? So this is fully observable, an example of fully observable environment. In contrast, we have this partially observable environment in self-driving car. The reason is because, for instance, right, of course, the self-driving car are able to look into whatever it is like the sensors could take. For example, there is a car over here, maybe there is a human being over here, but it will not be able to see things which are outside of the sensor range, right? Let's say maybe there is an airplane over here, right? I want to drive an airplane, but like it's bad. But it's an airplane, by the way. Let's say there's an airplane, right? Like far above the cloud, for example. Then this self-driving car, like in this environment, the self-driving car will not be able to see it. That's why it's partially observable. like sometimes these things are important because maybe the information about the airplane's about to go down and then like gonna hit the car, but the car will not know because it's partial observable and it will not be able to notice that the airplane's actually going down. So that's what differentiates the fully observable and partial observable environments. It's about the information that are available to the agent. There's also another properties. It is between either deterministic or stochastic or strategic. So what does it mean? So let's just go to the example because probably it's easier to illustrate from example. So an example of deterministic environment is this one. So let's say some of you might have played some simple car games in Google Play, right? So this is a very simple car games in Google Play. You could drive a car up, down, left, right, for example. This is an example of a deterministic environment. So in a deterministic environment, what happens is if you press up, for example, right, then it's 100%, this car will be moving up here. If you press left, then 100% the car will be here. If you press right, 100% the car will be here. There is no randomness at all in terms of the outcome of what you do. In comparison, if you have this self-driving car, right? Let's assume that this self-driving car lives in a world where there is no one else. There is no other cars. There is no human beings. There is no one else. It's just like the car alone, right? Then it is a stochastic environment. It is a stochastic environment. The reason it is called stochastic is because there is an element of randomness inside. So for instance, let's say you steer the car like this way, right? You twist the wheel like this way. Then there is some kind of possibility that maybe your car actually is moving this way. Maybe your car is moving this way. Because maybe there is some odd things in the wheels, or maybe there is some weird things happening in the steering wheel or something, and nobody knows. But there is some elements of randomness, usually in real world, that that so happen in here in the stochastic environment. So stochastic means it's random. There is an element of randomness. In contrast, we also have this thing called strategic environment. Like a good example of strategic environment is this chess problem. This chess problem is strategic because it's very easy to know whether an environment is strategic or not. If there are other agents, other players that could also think and react when you do something, so it's strategized either against or for you, then it's actually a strategic environment. So the environment actually strategizes against you or for you, either being cooperative with you or trying to make you die or something, right? So that's what strategic environment is. So that's why chess is one of the examples. The other example, maybe if you play games like Counter-Strike or I don't know, like StarCraft, for example, those games where you try to shoot other people, right? Like those things are also strategic environment. This environment over here, this car environment, it could also be strategic. You could also thought about it as a strategic environment because there are other cars around, there are other people, and these other people and these cars actually reacts and strategize against you. They have their own will and intentions and thoughts that they want to, the way they're interacting with this environment. So that's why it could also be a strategic environment. Okay, any question before I move on about this properties of environment? Hopefully it's okay, right? Now, the other properties of environment is this thing called, an environment could either be episodic or sequential. So let's have a look into example again. So this is one example of episodic environment. So basically in this environment, right, it is an industrial robot. The task of the robot is, given a metal, right, it tries to flip it. So if it's on the wrong direction like this, then it tries to grab it and then flip it this way. And then it will be on some kind of a production line. So whatever things that comes in front of it, it tries to flip it if it's in the wrong orientation. So that's what it is. It is an episodic environment. The reason is because the decision that it is currently making in terms of either flipping the thing in front of it actually does not depend on whatever it is that he has done before. No matter whether previously he has flipped 3 metal or flipped 5 metals, or maybe didn't flip properly, it doesn't matter. It doesn't affect the decision currently, because the decision currently in front of him, in front of the robot, it's independent of the past. So that's what episodic environment is. It's an episode. Oh, another episode. I have this metal. I have to flip it or not flip it. Oh, another episode again. Another metal. I'll have to flip it or not flip it. So that's why it's called episodic environment. In comparison, we have these two environments being a sequential environment. The reason is, let's say we have a look into this environment, right? This self-driving car environment, right? What happens is, let's say suddenly there is a human like in front of your car. Let's say it jumps in front of you, like this human being. Then the decision whether you should hit this pedal, whether you have to hit the pedal hard or you have to hit it, like slowly, it depends on your previous actions. So if in the previous actions, let's say this is your car, right? You have been speeding up, like you're like very, very fast, right? Then your action right now, upon seeing this human being, you have to hit the brake very, very hard. So your decision currently actually is affected by whatever happens in the past. So that's why it's a sequential environment, because the sequence of actions leading to the current state that you're in actually affects your decision right now. So that's why it's called sequential. In contrast, right, if, for example, your car is driving very slowly, then there is a human being, then you just, press the brake very slowly, and you should be still safe. So that's why, since the decision right now depends on the decision that you have made before and the state that you have been before previously, then it becomes a sequential problem. It is also the same with this chess problem, because in chess, whatever actions that you have done in the past, whether, for example, right, you let your, I don't know, like this piece over here, get eaten, then I want to do something about that piece, and there's nothing you can do about it right now. You can only regret that you let that piece to be eaten. So that's the reason why it's also called sequential, because you have sacrificed a king, and now you want to do something with that king. There's no way to do it. So your past influence your future. It's called sequential. Another type of environment called properties of environment, static or dynamic environment. And an example of static environment or semi-dynamic environment is this chess problem. The static environment basically means that, let's say, you are, like this is your board, like the other player has already moved, and then now it's time for you to move. And you decided not to move. You decided to go and grab a coffee and then finish a PhD degree, and then you come back. And then the chessboard will not move at all. So that's what it means to be static environment. It doesn't change whatever you do. Like if you don't do anything with that chessboard, it will not automatically do something. It doesn't, the chessboard will not suddenly solve itself, for example. So that's what it means that it's to be static. It could also be semi-dynamic for this chess problem. If, for example, right, this is a game of chess with some timer. So your score actually depends on the timer. So you think about it, you leave for a PhD degree, you came back, the timer runs out, and your score will be 0. So that's why, if there is something changing, then it becomes semi-dynamic. Like the state itself, like the board itself doesn't change. It's just that the reward that you'll get, it changes. Then it is called semi-dynamic. In comparison, we also have this environment called dynamic environment. Let's say you have a person over here, right, in front of you. Your car is moving fast, there is a person in front of you, and then you stop and think. You think through it. You take, I don't know, maybe 2 days to think about it, and then it'll be already too late. You'll be in prison. So that's why, it's called dynamic environment, because, you hit the car, and then, police will take you, and, those things happen in your life because it is a dynamic environment. You cannot just, stop and think about what to do. Okay, any questions about this static and dynamic environment? All right, hopefully it's clear. The examples are kind of odd, but hopefully it's clear. Okay. We also have another properties of environment, which is called discrete or continuous environment. So let's have a look into it. So this environment over here, the chess environment, is called discrete environment, because the pieces, the amounts of it, the move of the pieces, there are limited number of distinct possibility of the configuration, right? So this piece could only be either in here or in here or in here or in here. Like there are only like limited possibilities of where it can be. Like this piece also could also be only in like some places. So it is discrete because like there are only finite possibilities of like this configuration of the chess. In contrast, we have this thing called the continuous environment. It's continuous because the car position could be anywhere. It could be 1.756 centimeters in front of you. Another car could be 1.9995 centimeters in front of you. There are continuous number of like possible location that your car could be in. So it is called a continuous environment. So it's a continuous in the sense that the configuration of your environment could be, like there is no way to count it, basically. We also have this thing called single agent, multi-agent. I think probably pretty easy. So this one is single agent, right? Because there is only one agent. The agent interacts whether flipping or not flipping. That's all. We also have a multi-agent environment. This one is multi-agent. This one is also multi-agent environment because, like like in chess you have an opponent. In a car you also have not really opponent. You have other people, other cars. So those things are like other agents. So that's why it's called multi-agent environment. Okay. Any questions so far? Okay, hopefully. Now that we're done talking about the environment, right? Then I think it's time for us to look into the function, the agent function itself. Like how we could actually build, what kind of, like is there any different types of agent function that we could build upon? So, but first I think we have to have like some kind of formalism. Like the agent function basically maps percept histories to action. So this function f is the agent function. So it takes in percept histories. It means that, like in the case of self-driving car, then you'll get, let's say, your LiDAR data, right? You have 10 seconds of your LiDAR data. That'll be your history. You have LiDAR data at time step 1, LiDAR data like at a second. You have like the 3rd second, the 4th second, up to the 10th second that you're currently looking at. So those are like history of percepts. So that's that. Or maybe you have videos feed, right? Like your car is like Tesla, doesn't have LiDAR, it has camera. So it will take in videos, right? Feed coming from outside. And videos basically just sequence of images. So the percepts basically is the history of that sequence of images. So maybe 10 images like in the past or something. And then based on that, you'll take an action. Maybe the car will be moving left, moving right, like accelerate, decelerate, whatever. And then the agent program usually runs in some kind of physical architecture. Maybe like your car, your car has an onboard computer and so on. And the function itself, now we talk about the function itself, it has like different kind of structure. And this agent function actually completely specifies an agent. So if you want to design an agent, you just have to design the agent function. Because these sensors and these actuators, we can just leave it to, I don't know, some engineers out there. But us, we only care about, what's got this agent actually behaving, right? How the agent actually think, which is inside of this agent function. So if you define the agent function, then your AI is more or less complete. And there are many types of agent functions. So here I'm going to show you some common agent function structures. So it could be like simple reflex agents, model-based reflex agents, goal-based agents, utility agents, learning agents, and so on. So I'm going to go through each one right now. So simple reflex agent basically is an agent where it only has some kind of a very simple condition action rule. So it has some kind of rule, and based on that rule and the percept that comes in, like the state that it is currently in, it will behave. So for instance, right, in here, like the agent is, like this is the state that we're currently seeing, right? Then a simple reflex agent will look into the condition action rule. So, okay, let's see like this one first. If up is empty, then I go up. Oh, turns out up is not empty, so I'm not going up. Let's have a look into the next one. Or if right is empty, then I go right. Oh, this right is actually empty, but it's lava, I will die. But, I mean, the direction is to go right, so I'm going right. So then it will go right and it will die, basically. So it will go right. So this is what simple reflex agent basically is. So based on a bunch of rules, it will decide what it will do. So this is simple reflex agent. We have slightly more advanced agent like structure, which is called model-based agent. And the idea is that we still have the condition action rules. So based on the condition, we should maybe like do something, right? But in the model-based agent, what happens is it is able to kind of like, it has a model of the environment. So a model of the environment means that it has some kind of simulation of the environment. So it knows what happens if it moves up, if it knows what happens if it moves down, and so on. So in this case, right, like, okay, let's see what happens if I were to move left, right? Let's say what happens if I move left. Oh, if I move left, turns out I'm actually in this position over here, in this position over here. And then based on the condition action rule, oh, maybe let's not execute the condition action rule first. Let's continue again, like assuming that we move right instead, right? So if we move right, let me just delete this so that it's not terminated. It doesn't terminate too fast, otherwise it's not fun. So let's say I want to move right instead, right? So I want to move right. Then if I move right, then what happens is I will be in here. And being in here means that I will die because this is lava, right? This is lava. So I will look into my condition action rule. If goal, pick the action. It is not a goal, so I will not pick the action. Else, if not die, pick the action. Oh, I'm actually going to die, so I will not pick the action. So it's a bit smarter. And then let's try to move up. Oh, moving up actually, oh, okay, let's not move up. Let's move down. Let's try to move down, for example, right? To move down, then what happens is I will be going to be in this position over here. And I'll check again my condition action rule. Is it a goal? No, it's not a goal. Am I going to die? No, you're not going to die. So we'll be just picking this one. So the agent will be outputting in the actuators to move down. So it's slightly smarter. It is able to know what the environment will, what will happen if it does certain action. It has this thing called a model of the environment. It has a model of the environment or a simulation of the environment. Another type of agent, which is more sophisticated, is this thing called goal-based agent. So in the goal-based agent, usually we will specify what the goal of the agent is. So in this case, oh, we want to get into this green box over here. This is the goal of the agent, right? And then the agent is also endowed with the capability to know what happens if it does certain things. So let's say, oh, I will try to move left. Oh, moving left actually means that I will be ending up in here. I'll try to move up. Moving up actually means that I will be not going anywhere because, up there is nothing there. I can also try to move right. Moving right means that I will be, moving right means I'm going to die, so not a good idea. Moving down means that I will be ending up in here. And then it will do that again. Maybe, oh no, okay, I will try to do like all the possible actions from here. I'll do like all possible actions starting from this state and from this state. And maybe from this state, I will do another possible actions, right? So I'm in here. Oh, let's try to move right. Moving right actually means that, oh, I will be ending up in my goal. Since I'm in my goal, then the best course of action is, oh, actually to move down. So this is the action that you took the first time. So that's what goal-based agent is. It has a notion of goal. It will do like some kind of look ahead. It will imagine what happens if it does these things, if it does the other thing. And then if eventually it reaches a goal, the goal that it has set out to go to, then it will pick the action that leads to that goal. So that's what goal-based agent basically is. Before I move on, I think maybe good to pause a little bit. Any questions about this? Okay, hopefully. Can I see some nods if it's okay? Okay. I see like some shakes as well. Like, any questions though? Yeah. More complex what? Yeah, it's more complex, right? So if you see like in the simple reflex agent, like the part over here, right, it's not this complicated, right? So it doesn't have the model of the world. It cannot really simulate and know what happens if it does certain things. So it's more complex than the simple reflex agent. And in particular, the way it is being complex is that it is able to simulate what's going to happen into the future. And not only that, it knows like where it should actually go. So once it identifies that it actually reaches a certain goal, then it will try to get to that goal by backtracking. Oh, actually, I came from here. I also came from here, and finally, you reach to the first action that you do. Make sense? Yeah. Okay. So another type of agent, agent structure, is this thing called utility-based agent. And the main idea of utility-based agent is very similar to the goal-based agent, but instead of having goal, what happens in utility-based agent is basically you define the utility or the value or the reward in being in a certain state. For instance, right? Let's say I am in this state over here, which is there is nothing happening. Then maybe I will assign a value or utility of 0 because it doesn't really benefit me to be in this state. Let's say I am in a different state, and I'm in the state here, right? It's in the green one. I want to go to that green one. Maybe I will assign a reward of 100s, right? Oh, another possible state is maybe I'm in here, right? In the red, right? Say, right? In the red. Then if I'm in the red, then I will assign negative 100s. So it has this kind of, like it has the notion of value, the notion of utility, and being in a certain state. So if it's in a good state, it will assign higher utility to that state. So 100 utility for being in a good state, negative 100 utility for being in a bad state, like in this red state, negative 100 utility. So based on the utility, then it will try to maximize its utility. So the way it maximizes utility is similar to the goal-based agent, which is by doing a look ahead. So let's say, I move left. If I move left, then what happens is I'm going to go here. If I move up, I will be going here. If I move right, then I will be going there. If I move down, then I will be going here. If I move right from here, then I will be going there, finally into the goal. Then what happens here basically, of course there are like a bunch more things happening, right? Like in here you could actually go to some other places. But what this utility-based agent does basically, it will assign the appropriate value for each of the state. So here is, there is nothing in here, so it will assign 0 value. There is, the agent actually dies in here right, after moving right. So moving right, it causes the agent to die here. So it will assign negative 100s. And then here is the goal, so it will assign like 100 utility over here. And then what it does is it will, kind of like backtrack and see what is the value of the previous state. So actually, if you go to this state, this will eventually lead you to a utility of 100. So you maximize over here, you get 100. And then, this one, eventually, if you take this action and you take this action, it will maximize its utility because it gets like 100 utility. So that's the idea, or 100 value. So these actions here, which is going down, is the best actions that you could take based on the utility that you'll get. Because otherwise, the other options would be either leading you to death with negative 100 utility or leading you to someplace else. So this is utility-based agent, slightly more complicated than the goal-based agent. The goal-based agent, yeah. Any questions? Yeah. Right. So the question is, so the simple reflex agent seems to be not really too useful, right? So the way you're actually designing your agent, right, you should look into the problem at hand. You should not just simply throw very complicated things into the problem if it's just like very simple agent that you want to build. Let's say you want to build just something like a Roomba robot, right? Like the robot that cleans up the floor. You don't actually need to have the AI agent that is capable in solving Go, for example, right? With this, utility-based agents and all these like weird things that you throw in, right? So again, like it depends on the case-by-case basis, yeah. Okay, next is a learning agent. The idea of learning agent basically is, the agent will be interacting with the environment, right? So the agent will be interacting with the environment, and based on these interactions, it will produce some kind of trajectories, right? For example, like from here, it will go maybe down, maybe it will go right, and it will get certain, like it's good, like this is a good plan. And maybe it will try to go left. If it goes left, then it goes this way, and then it will be stuck, and it will try to go this way, and it will try to go maybe this way, and so on. So what happens in the learning agent is you have a bunch of data, you have a bunch of interactions with the environment, and based on that interactions with the environment, you'll try to learn about, like being in a certain state. What is the value in being in a certain state? In performing certain actions. So maybe after, going through a bunch of different like episodes right here, right? Like from starting point, then you'll be able to learn that, oh, it is most likely for me that going down is the best course of action. So the main idea is that it has these learning components, and these learning components will help agent to kind of get the intuition that, oh, moving down in this particular state is the best course of action, or moving left is the best course of action. So that's the main idea. In here, we're not like going into details on the learning agent because like that would be like another topic. There is also like I said, right, there are many, many other types of agent structures. We could also do like combinations of common agent structures. For instance, in AlphaGo, so in AlphaGo, right, what happens is that it is actually a combination of utility-based agent. So, like it has this kind of like look ahead, like based on this, and then like assign some value. If it wins, then it got like 100. If it loses, then it got negative 100. If it wins again, like 100, and so on, right? So AlphaGo has this utility structure in it. But at the same time, it also has a learning component. So instead of like looking ahead until it eventually reaches the end of the game, either winning or losing, AlphaGo actually just stops in here, in the middle, before finishing the game, and then uses neural networks, basically, for the learning component of it. So it mixes and matches between learning and also utility-based agent. So that's why I think like the main idea in here is not for me to show you that AlphaGo does it this way, but it's just to illustrate to you that you can actually mix and match things, and probably you could get better results doing that way, depending on the problem. Okay, any questions about properties of, agent structures, structure of agents? Any questions? Yeah, go ahead. So the question is, what is the difference between learning agent and goal-based agent? Learning agent takes in like a bunch of data, and then based on that data, interactions with the environment, it will try to, you can think of it like gain an intuition on what action is the best to perform in a certain state. In a goal-based agent, it has the model of the environment. It has like the simulation of the environment. And based on that simulation, it knows what happens if it does certain things. Let's say if it moves to the forward, then it will end up in this state. If it moves backward, it will end up in this state. And based on that, then it will be able to, let's say, right, the goal of this agent, me, is to reach to that point, right? The goal-based agent will be able to do this. Oh, not goal yet. Okay, I'll go back. Oh, finally, I reached my goal. Okay, how come I ended up in my goal here? Let me see what happens before I got here. Oh, I was actually in here moving forward. I was actually in here moving slightly to the right side. And I was actually, at the very beginning, I was here, and I moved forward. So what I do right now, I should be moving forward. So that's what goal-based agent actually does. It will just like look through the possibilities and simulate the environment and see if it reaches the goal eventually, it will try to backtrack and see like, oh, actually I started performing this action that could eventually lead me to the goal. Does that make sense? Okay. Any other questions before I move forward? Okay. Now, coming back to the self-driving car example, right? There is another thing which an AI agent needs to take care of when it's operating in the environment. The thing which it has to take care of is this trade-off between exploration and exploitation. So if you are learning about AI, then you'll be seeing this term exploitation, exploration trade-off very, very often. The idea between exploration and exploitation basically means that whether, let's say I'm a self-driving car, whether I should explore and learn more about the world, or whether I should exploit. It means that I should maximize my gain by utilizing the current information that I know about the world. So just to give you an example, right? Let's say, right, this self-driving car, it has the choice. So usually, this self-driving car will go this way to reach its destination. It knows what the fuel cost is to go that way, and it will be, at least based on the knowledge of this car, it will be very efficient to go to this route over here. So if it were to do that and pick the usual route that it thinks, based on the knowledge that it has currently, is good, then it is called exploitation. However, exploitation sometimes is not, it's not the best possible things that you could do. It is possible that there might be another route, maybe this route, that could lead you to your destination much, much faster. But it's just that you haven't been to that route and you don't know. So that's why sometimes it is good for you to explore and learn more about the world and update your understanding about the world. And eventually, maybe in the case of the self-driving car, it tries to explore, and then it turns out, oh, previously it takes me 10 hours, it becomes maybe 5 hours. Then next time, what I will do is I will use this information to go and make a decision. So that's what exploration and exploitation means. However, there is a cost in doing exploration, because it is also possible that going this way actually leads to, maybe a roadblock, or there is no road going from there to your destination, right? So you could be paying a huge penalty by, trying to explore. So that's why there is this need of balance between exploration and exploitation. Sometimes maybe it's good to explore, sometimes it's good to exploit, and you have to kind of try to balance between these two. And your AI agents, just like human beings, have to be able to balance these two as well. Another example, we're very close to our life, right, is when we're going to supermarket. We run out of noodles, instant noodles. We go to supermarket, and then we are given, like this choice, whether we should go and pick like random instant noodles with the hope that we found the ultimate instant noodles. Or in this case, this is called exploration, because let's say in this case, right, for the sake of argument, we have our favorite instant noodles, let's say, it's called Indomie. This is the best instant noodles. Or we should just exploit and just buy Indomie again. This is also another option. So again, like this is another simple example of exploration versus exploitation. So exploration in this case, trying these noodles, sometimes it will be bad. You'll have unpleasant feelings, or the taste could be very bad. But sometimes you will hit the jackpot and then, oh, these noodles, fantastic, ultimate instant noodles, for example, right? Okay, so any questions? This is almost done. The lecture is almost done. Any questions? Yeah, for some reasons, there is no more questions. There is, any questions? Yeah, if you have good question, please, upvote it so that it surfaces and I would be able to see it. Okay, so I think I see some new questions here, right? Are there remote lecture options for students unable to attend physical lectures? There is a remote lecture option, which is in webcast, like I said, but then there is a delay of 1 minute, which is not good, because if you want to participate in the class, then probably you have to keep looking into your phone, and every time it refreshes and because some new questions comes up, you have to answer it, right? Because there is a delay. Because if you just keep looking into your screen, then probably you'll miss out that activities. Asking for overseas friends. Is the current Zoom link meant to be not streaming anything? Okay, so my previous plan was to use Zoom because I thought that there might be some benefits in doing it, but I ended up, I will think about it again, but I think probably we'll be using the webcast feature from the I think Panopto instead, because it's automatic. It will be recorded automatically, and it's very nice to use, although there is a delay, yeah. So I think before we end the lecture, it's good for us to go and have another quiz. So there is a quiz. Make sure to look into your phone because the quiz will be starting now. So open your polev.com and we'll start the last quiz of the day. So the quiz is about tic-tac-toe, by the way. For those of you who are not familiar with tic-tac-toe basically is this game where you have either O or X. And let's say you play as O, right? Then your opponent plays as X. And what you do is you're going to put in O, and your opponent will put in X. And you put in maybe another O, and your opponent will do X. And then you put another O. Then if you make this diagonal, or maybe you make this, diagonal, or make this horizontal, or maybe you make this vertical like this, like horizontal like this maybe, then you'll win the game. So that's what tic-tac-toe is. Now the question is, what are the properties of the task environment in tic-tac-toe? So please answer that in your phone. Observability. Is it fully observable or is it partially observable? Please answer it in your phone. Repeat that again. You have not started what? But it's starting, right, already, right? But I've started the presentation. Is it, I don't know, like, Polyv has been very buggy. You're not able to see it, is it? You're still not able to see it even now. Ha. Okay, let me do it manually then. So I will start the thing now. Let me see if we can do this. Okay, so I'm using this polev. What are the properties of task environment? Can you see it now? All right. Yeah, it's very buggy actually, polev. Maybe I should not use the PowerPoint integration next time. Yeah. So let's start. Okay, cannot click next. Observability. Is it fully observable or is partially observable? There is a timer on the bottom right corner over there. Okay, so it's done. Let's see what it looks like. Okay, so observability, most of you got it right. So tic-tac-toe is fully observable because you can see, like the O's and the X's, everything, all the, board information is available for you. Next, what about, oh, this is the leaderboard. A, E, that's really odd. Anyways, let's continue. Is it deterministic, stochastic, or strategic? Okay, it's done. Yeah, so it is strategic. Because again, like it's a two-player games. Like the other player is trying to beat you as well. So the other player actually strategically trying to, like do something to make you lose. So that's strategic. Is it what is? Okay, leaderboard, and is it static, dynamic, or semi-dynamic? Okay, let's see the answer. Yeah, it is a static environment. In tic-tac-toe, you can leave it and grab a coffee, you come back, the board configuration doesn't change, so it's static environment. Finally, I think this one is the last one. Is it episodic? Oh no, this is not the last one. Episodic or sequential? Okay, so it's like a few of you actually answer with episodic, but the actual answer is actually sequential, because in tic-tac-toe, once you put in your O's, right, there is no way for you to, like you have to live with that basically, right? And then your decision right now, whether you put in O or, like in one place or the other, depends on what you have done before. So that's why it's sequential. I think this is probably the last one. Let me see. Is it single agent or multi-agent? I think this is probably the easiest one, because it's quite obvious what's the answer for this one. Okay, oh, that's really odd. Like, it's really odd, actually. I didn't expect this, but 50% of you actually think that it is single agent, although there are multiple agents, quite obvious. So the reason why it's multi-agent, for those of you to pick single agent, is because there are other players, right, in the game, right? It's the two-player game, so there are two agents playing, right? Yeah, I think that's all, and this is the final standing. I think most of you got it right. Like a lot of you got 5,000 points, so these are the winners. Yep. So I think let's go back to our slide again. Okay, let me just close up the lecture today by summarizing it. So we talk about AI, which is basically computers trying to behave like humans. We talk about peace framework, which consists of performance, measuring the performance of the agent, environment, which define the agent, what it can do and cannot do, actuators, which is the outputs, and the sensors, which is the input. We also talk about the agent functions. In particular, agent function actually is sufficient to define an agent. And common agent structures, these are some of them, and we talk about exploration versus exploitation. So, coming up next week, so we'll talk about how we could formulate search problems. We'll talk about uninformed search algorithms. We'll talk about informed search algorithms as well. And some other things that you have to do here, these are like the things that you have to do. So you have lecture trading 1, you have problem set 0, which is optional. These are the deadlines. You could also have a look into it in the cosmology. I think that's all for me. Thank you very much for joining me today. Hope to see you guys again next week. Bye-bye. If you have any questions, feel free to come forward, by the way.